A photograph shows an aerial view of buildings, trees, and a large area clear of vegetation, above which rises a plume of steam. Figure 16. Geysers are a dramatic display of thermodynamic principles in nature. Water deep within the underground channels of the geyser is under high pressure and heated to high temperature by magma. When a pocket of water near the surface reaches boiling point and is expelled, the resulting drop in pressure causes larger volumes of water to flash boil, forcefully ejecting steam and water in an impressive eruption. Credit, Modification of work by Yellowstone National Park. Chapter outline: 16. 1. Spontaneity. 16. 2. Entropy. 16. 3. The second and third laws of thermodynamics. 16. 4. Free energy. Among the many capabilities of chemistry is its ability to predict if a process will occur under specified conditions. Thermodynamics, the study of relationships between the energy and work associated with chemical and physical processes, provides this predictive ability. Previous chapters in this text have described various applications of thermochemistry, an important aspect of thermodynamics concerned with the heat flow accompanying chemical reactions and phase transitions. This chapter will introduce additional thermodynamic concepts, including those that enable the prediction of any chemical or physical changes under a given set of conditions. Learning objectives. By the end of this section, you will be able to distinguish between spontaneous and non-spontaneous processes, describe the dispersal of matter and energy that accompanies certain spontaneous processes. Processes have a natural tendency to occur in one direction under a given set of conditions. Water will naturally flow downhill, but uphill flow requires outside intervention, such as the use of a pump. Iron exposed to the Earth's atmosphere will corrode, but rust is not converted to iron without intentional chemical treatment. A spontaneous process is one that occurs naturally under certain conditions. A non-spontaneous process, on the other hand, will not take place unless it is driven by the continual input of energy from an external source. A process that is spontaneous in one direction under a particular set of conditions is non-spontaneous in the reverse direction. At room temperature and typical atmospheric pressure, for example, ice will spontaneously melt, but water will not spontaneously freeze. The spontaneity of a process is not correlated to the speed of the process. A spontaneous change may be so rapid that it is essentially instantaneous, or so slow that it cannot be observed over any practical period of time. To illustrate this concept, consider the decay of radioactive isotopes, a topic more thoroughly treated in the chapter on nuclear chemistry. Radioactive decay is by definition a spontaneous process in which the nuclei of unstable isotopes emit radiation as they are converted to more stable nuclei. All the decay processes occur spontaneously, but the rates at which different isotopes decay vary widely. Technetium-99m is a popular radioisotope for medical imaging studies that undergoes relatively rapid decay and exhibits a half-life of about 6 hours. Uranium-238 is the most abundant isotope of uranium, and its decay occurs much more slowly, exhibiting a half-life of more than 4 billion years, figure 16. 2. A graph of 2 lines is shown where the y-axis is labeled amount of isotope remaining %, and has values 0 through 100 in increments of 10 written along the axis. The x-axis is labeled time days and has values 0 through 7 in increments of 1 written along the axis. The first graph, drawn with a blue line, begins at the top left value of 100 on the y-axis and 0 on the x-axis and falls steeply over the first 3 minutes. Then the graphed line becomes almost horizontal until it reaches 7 minutes on the x-axis. The second graph, drawn in red, begins at the same point as the first, but remains perfectly horizontal with no change along the y-axis. A legend labels the red line as U-238 and the blue line as figure 16. Both U-238 and Tc-99m undergo spontaneous radioactive decay, but at drastically different rates. Over the course of 1 week, essentially all of a Tc-99m sample and none of a U-238 sample will have decayed. As another example, consider the conversion of diamond into graphite, figure 16. 3. C. Letter 1D460, diamond. C. Letter 1D460, graphite. The phase diagram for carbon indicates that graphite is the stable form of this element under ambient atmospheric pressure, while diamond is the stable allotrope at very high pressures, such as those present during its geologic formation. Thermodynamic calculations of the sort described in the last section of this chapter indicate that the conversion of diamond to graphite at ambient pressure occurs spontaneously. Yet diamonds are observed to exist and persist under these conditions. Though the process is spontaneous under typical ambient conditions, its rate is extremely slow. So, for all practical purposes, diamonds are indeed forever. Situations such as these emphasize the important distinction between the thermodynamic and the kinetic aspects of a process. In this particular case, diamonds are said to be thermodynamically unstable but kinetically stable under ambient conditions. Two pairs of images are shown. The left pair, labeled C, diamond, has a picture of a diamond held by a pair of pliers and a diagram of the molecular arrangement. The second pair, labeled C, graphite, has a picture of a large, black, slightly shiny rock and a diagram of 4 sheets composed of many atoms arranged in large squares in a stacked arrangement with space between each. Figure 16. 3. The conversion of carbon from the diamond allotrope to the graphite allotrope is spontaneous at ambient pressure, but its rate is immeasurably slow at low to moderate temperatures. This process is known as graphitization, and its rate can be increased to easily measurable values at temperatures in the 1000–2000 K range. Credit diamond photo. Modification of work by Fancy Diamonds / Flickr. Credit graphite photo. Modification of work by Images of Elements. Carbon, PHP. Dispersal of matter and energy. Extending the discussion of thermodynamic concepts toward the objective of predicting spontaneity. Consider now an isolated system consisting of 2 flasks connected with a closed valve. Initially, there is an ideal gas in one flask and the other flask is empty, P = 0. Figure 16. 4. When the valve is opened, the gas spontaneously expands to fill both flasks equally. Recalling the definition of pressure-volume work from the chapter on thermochemistry, note that no work has been done because the pressure in a vacuum is 0. Letter 1D464 equals minus letter 1D443 delta, letter 1D449 equals 0. Letter 1D443 equals 0 in a vacuum. Note as well that since the system is isolated, no heat has been exchanged with the surroundings. Q = 0. The first law of thermodynamics confirms that there has been no change in the system's internal energy as a result of this process. Delta letter 1D448 equals letter 1D45E plus letter 1D464 equals 0 plus 0 equals 0. The spontaneity of this process is therefore not a consequence of any change in energy that accompanies the process. Instead, the driving force appears to be related to the greater, more uniform dispersal of matter that results when the gas is allowed to expand. Initially, the system was comprised of one flask containing matter and another flask containing nothing. After the spontaneous expansion took place, the matter was distributed both more widely, occupying twice its original volume, and more uniformly, present in equal amounts in each flask. A diagram shows 2 two-sided flasks connected by a right-facing arrow labeled spontaneous and a left-facing arrow labeled non-spontaneous. Each pair of flasks are connected to one another by a tube with a stopcock. In the left pair of flasks, the left flask contains 30 particles evenly dispersed, while the right flask contains nothing and the stopcock is closed. The right pair of flasks has an open stopcock and equal numbers of particles in both flasks. Figure 16. 4. An isolated system consists of an ideal gas in one flask that is connected by a closed valve to a second flask containing a vacuum. Once the valve is opened, the gas spontaneously becomes evenly distributed between the flasks. Now consider 2 objects at different temperatures. Object X at temperature Tx and object Y at temperature Ty, with Tx, Ty, figure 16. 5. When these objects come into contact, heat spontaneously flows from the hotter object X to the colder one Y. This corresponds to a loss of thermal energy by X and a gain of thermal energy by Y. Letter 1d45e, X0, a ND letter 1d45e, Y equals minus letter 1d45e, X0. From the perspective of this two-object system, there was no net gain or loss of thermal energy. Rather, the available thermal energy was redistributed among the two objects. This spontaneous process resulted in a more uniform dispersal of energy. Two diagrams are shown. The left diagram is comprised of two separated squares. The left is red and labeled X, and the right is blue and labeled Y. Below this diagram is the label T subscript X, a greater than sign T subscript Y. The right diagram shows the boxes next to one another, shaded red on the left, blue on the right, and blended red and blue together in the middle. The left box is red and labeled X. The right is blue and labeled Y, and a right-facing arrow labeled heat is written above them. Below this diagram is the label X and Y in contact. Figure 16. 5. When two objects at different temperatures come in contact, heat spontaneously flows from the hotter to the colder object. As illustrated by the two processes described, an important factor in determining the spontaneity of a process is the extent to which it changes the dispersal or distribution of matter and/or energy. In each case, a spontaneous process took place that resulted in a more uniform distribution of matter or energy. Example 16. 1. Redistribution of matter during a spontaneous process. Describe how matter is redistributed when the following spontaneous processes take place. A. A solid sublimes. B. A gas condenses. C. A drop of food coloring added to a glass of water forms a solution with uniform color. Solution. This figure has three photos labeled A, B, and C. Photo A shows a glass with a solid in water. There is steam or smoke coming from the top of the glass. Photo B shows the bottom half of a glass with water sticking to its outside surface. Photo C shows three images of the same container. The first shows a clear liquid in the container. The second shows a red liquid mixing with the clear liquid in the container. The third shows a red liquid. Figure 16. 6. Credit A. Modification of work by Jenny Downing. Credit B. Modification of work by Fuzzy Jerds/Flicker. Credit C. Modification of work by Paul A. Flowers. A. Sublimation is the conversion of a solid, relatively high density, to a gas, much lesser density. This process yields a much greater dispersal of matter, since the molecules will occupy a much greater volume after the solid-to-gas transition. B. Condensation is the conversion of a gas, relatively low density, to a liquid, much greater density. This process yields a much lesser dispersal of matter, since the molecules will occupy a much lesser volume after the gas-to-liquid transition. C. The process in question is diffusion. This process yields a more uniform dispersal of matter, since the initial state of the system involves two regions of different dye concentrations, high in the drop of dye, 0 in the water, and the final state of the system contains a single dye concentration throughout. Check your learning. Describe how energy is redistributed when a spoon at room temperature is placed in a cup of hot coffee. Answer. Heat will spontaneously flow from the hotter object, coffee, to the colder object, spoon, resulting in a more uniform distribution of thermal energy as the spoon warms and the coffee cools. Learning objectives. By the end of this section, you will be able to define entropy, explain the relationship between entropy and the number of microstates, predict the sign of the entropy change for chemical and physical processes. In 1824, at the age of 28, Nicholas Leonard Sadi Carnot, figure 16. 7. Published the results of an extensive study regarding the efficiency of steam heat engines. A later review of Carnot's findings by Rudolf Clausius introduced a new thermodynamic property that relates the spontaneous heat flow accompanying a process to the temperature at which the process takes place. This new property was expressed as the ratio of the reversible heat, Q-rev, and the Kelvin temperature, T. In thermodynamics, a reversible process is one that takes place at such a slow rate that it is always at equilibrium, and its direction can be changed. It can be reversed by an infinitesimally small change in some condition. Note that the idea of a reversible process is a formalism required to support the development of various thermodynamic concepts. No real processes are truly reversible. Rather, they are classified as irreversible. A portrait of Rudolf Clausius is shown. Figure 16. 7a. Nicholas Leonard Sadi Carnot's research into steam-powered machinery, and b. Rudolf Clausius's later study of those findings led to groundbreaking discoveries about spontaneous heat flow processes. Similar to other thermodynamic properties, this new quantity is a state function, so its change depends only upon the initial and final states of a system. In 1865, Clausius named this property entropy S, and defined its change for any process as the following. Delta letter 1 D446 equals letter 1 D45 rev, letter 1 D447. The entropy change for a real, irreversible process is then equal to that for the theoretical reversible process that involves the same initial and final states. Entropy and microstates. Following the work of Carnot and Clausius, Ludwig Boltzmann developed a molecular-scale statistical model that related the entropy of a system to the number of microstates, W, possible for the system. A microstate is a specific configuration of all the locations and energies of the atoms or molecules that make up a system. The relation between a system's entropy and the number of possible microstates is letter 1 D446 equals letter 1 D45 ln, letter 1 D44a, where k is the Boltzmann constant 1, 38 times 10⁻23 jk. As for other state functions, the change in entropy for a process is the difference between its final SF and initial C values. For processes involving an increase in the number of microstates, WFY, the entropy of the system increases and delta's 0. Conversely, processes that reduce the number of microstates, WFY, yield a decrease in system entropy, delta's 0. This molecular-scale interpretation of entropy provides a link to the probability that a process will occur as illustrated in the next paragraphs. Consider the general case of a system comprised of n particles distributed among n boxes. The number of microstates possible for such a system is nn. For example, distributing 4 particles among 2 boxes will result in 24 equals 16 different microstates, as illustrated in Figure 16. 8. Microstates with equivalent particle arrangements, not considering individual particle identities, are grouped together and are called distributions. The probability that a system will exist with its components in a given distribution is proportional to the number of microstates within the distribution. Since entropy increases logarithmically with the number of microstates, the most probable distribution is therefore the one of greatest entropy. 5 rows of diagrams that look like dominoes are shown and labeled a B, C, D, and E. Row A has one domino that has 4 dots on the left side, red, green, blue, and yellow in a clockwise pattern from the top left, and no dots on the right. Row B has 4 dominoes, each with 3 dots on the left and 1 dot on the right. The first shows a domino with green, yellow, and blue on the left and red on the right. The second domino has yellow, blue, and red on the left and green on the right. The third domino has red, green, and yellow on the left and blue on the right, while the fourth has red, green, and blue on the left and yellow on the right. Row C has 6 dominoes, each with 2 dots on either side. The first has a red and green on the left and a blue and yellow on the right. The second has a red and blue on the left and a green and yellow on the right, while the third has a yellow and red on the left and a green and blue on the right. The fourth has a green and blue on the left and a red and yellow on the right. The fifth has a green and yellow on the left and a red and blue on the right. The sixth has a blue and yellow on the left and a green and red on the right. Row D has 4 dominoes, each with 1 dot on the left and 3 on the right. The first domino has red on the left and a blue, green, and yellow on the right. The second has a green on the left and a red, yellow, and blue on the right. The third has a blue on the left and a red, green, and yellow on the right. The fourth has a yellow on the left and a red, green, and blue on the right. Row E has 1 domino with no dots on the left and 4 dots on the right that are red, green, blue, and yellow. Figure 16. 8. The 16 microstates associated with placing 4 particles in 2 boxes are shown. The microstates are collected into 5 distributions, A, B, C, D, and E, based on the numbers of particles in each box. For this system, the most probable configuration is one of the 6 microstates associated with distribution. C, where the particles are evenly distributed between the boxes, that is, a configuration of 2 particles in each box. The probability of finding the system in this configuration is 616, or 38. The least probable configuration of the system is one in which all 4 particles are in one box, corresponding to distributions A and E, each with a probability of 116. The probability of finding all particles in only one box, either the left box or right box, is then 116 plus 116 equals 216, or 18. As you add more particles to the system, the number of possible microstates increases exponentially 2n. A macroscopic, laboratory-sized system would typically consist of moles of particles, n 1023, and the corresponding number of microstates would be staggeringly huge. Regardless of the number of particles in the system, however, the distributions in which roughly equal numbers of particles are found in each box are always the most probable configurations. This matter dispersal model of entropy is often described qualitatively in terms of the disorder of the system. By this description, microstates in which all the particles are in a single box are the most ordered, thus possessing the least entropy. Microstates in which the particles are more evenly distributed among the boxes are more disordered, possessing greater entropy. The previous description of an ideal gas expanding into a vacuum, figure 16.4, is a macroscopic example of this Pardic-Linabox model. For this system, the most probable distribution is confirmed to be the one in which the matter is most uniformly dispersed or distributed between the 2 flasks. Initially, the gas molecules are confined to just one of the 2 flasks. Opening the valve between the flasks increases the volume available to the gas molecules and, correspondingly, the number of microstates possible for the system. Since WFY, the expansion process involves an increase in entropy, delta 0, and is spontaneous. A similar approach may be used to describe the spontaneous flow of heat. Consider a system consisting of 2 objects, each containing 2 particles and 2 units of thermal energy, represented as asterisk in figure 16.9. The hot object is comprised of particles A and B and initially contains both energy units. The cold object is comprised of particles C and D, which initially has no energy units. Distribution A shows the 3 microstates possible for the initial state of the system, with both units of energy contained within the hot object. If one of the 2 energy units is transferred, the result is distribution B, consisting of 4 microstates. If both energy units are transferred, the result is distribution C, consisting of 3 microstates. Thus, we may describe this system by a total of 10 microstates. The probability that the heat does not flow when the 2 objects are brought into contact, that is, that the system remains in distribution A, is 310. More likely is the flow of heat to yield one of the other 2 distribution, the combined probability being 710. The most likely result is the flow of heat to yield the uniform dispersal of energy represented by distribution B, the probability of this configuration being 410. This supports the common observation that placing hot and cold objects in contact results in spontaneous heat flow that ultimately equalizes the objects' temperatures. And again, this spontaneous process is also characterized by an increase in system entropy. 3 rows labeled A, B, and C are shown, and each contains rectangles with 2 sides where the left side is labeled A and B, and the right is labeled C and D. Row A has 3 rectangles where the first has a dot above and below the letter A, the second has a dot above the A and B, and the third, which has a dot above and below the letter B. Row B has 4 rectangles. The first has a dot above A and C, the second has a dot above A and D, the third has a dot above B and C, and the fourth has a dot above B and D. Row C has 3 rectangles. The first has a dot above and below the letter C, the second has a dot above C and D, and the third has a dot above and below the letter D. Figure 16.9. This shows a microstate model describing the flow of heat from a hot object to a cold object. A, before the heat flow occurs, the object comprised of particles A and B contains both units of energy and as represented by a distribution of 3 microstates. B. If the heat flow results in an even dispersal of energy, 1 energy unit transferred, a distribution of 4 microstates results. C. If both energy units are transferred, the resulting distribution has 3 microstates. Example 16. 2. Determination of deltas. Calculate the change in entropy for the process depicted below. A diagram shows one rectangle with 2 sides that has 4 dots, red, green, yellow, and blue written on the left side. A right-facing arrow leads to 6 more 2-sided rectangles, each with 2 dots on the left and right sides. The first rectangle has a red and green dot on the left and a blue and yellow on the right, while the second shows a red and blue on the left and a green and yellow on the right. The third rectangle has a red and yellow dot on the left and a blue and green on the right, while the fourth shows a green and blue on the left and a red and yellow on the right. The fifth rectangle has a yellow and green dot on the left and a blue and red on the right, while the sixth shows a yellow and blue on the left and a green and red on the right. Solution. The initial number of microstates is 1, the final 6. Delta letter 1d446 equals letter 1d45a letter 1d44ac, letter 1d44a, a equals 1. 38 times 10 minus 23, j/k times ln 61 equals 2. 47 times 10 minus 23, j/k. The sign of this result is consistent with expectation. Since there are more microstates possible for the final state than for the initial state, the change in entropy should be positive. Check your learning. Consider the system shown in Figure 16. 9. What is the change in entropy for the process where all the energy is transferred from the hot object Ob to the cold object Cd? Answer. 0 Jk. Predicting the sign of deltas, the relationships between entropy, microstates, and matter energy dispersal described previously allow us to make generalizations regarding the relative entropies of substances and to predict the sign of entropy changes for chemical and physical processes. Consider the phase changes illustrated in Figure 16. 10. In the solid phase, the atoms or molecules are restricted to nearly fixed positions with respect to each other and are capable of only modest oscillations about these positions. With essentially fixed locations for the system's component particles, the number of microstates is relatively small. In the liquid phase, the atoms or molecules are free to move over and around each other, though they remain in relatively close proximity to one another. This increased freedom of motion results in a greater variation in possible particle locations, so the number of microstates is correspondingly greater than for the solid. As a result, liquid S-solid and the process of converting a substance from solid to liquid, melting, is characterized by an increase in entropy, delta 0. By the same logic, the reciprocal process, freezing, exhibits a decrease in entropy, delta 0. 3 stoppered flasks are shown with right and left-facing arrows in between each. The first is labeled above as delta S greater than 0, and below as delta S less than 0, while the second is labeled above as delta S greater than 0, and below as delta S less than 0. A long, right-facing arrow is drawn above all the flasks and labeled increasing entropy. The left flask contains 27 particles arranged in a cube in the bottom of the flask and is labeled crystalline solid below. The middle flask contains 27 particles dispersed randomly in the bottom of the flask and is labeled liquid below. The right flask contains 27 particles dispersed inside of the flask and moving rapidly and is labeled gas below. Figure 16. 10. The entropy of a substance increases delta 0 as it transforms from a relatively ordered solid to a less ordered liquid and then to a still less ordered gas. The entropy decreases delta 0 as the substance transforms from a gas to a liquid and then to a solid. Now consider the gaseous phase, in which a given number of atoms or molecules occupy a much greater volume than in the liquid phase. Each atom or molecule can be found in many more locations, corresponding to a much greater number of microstates. Consequently, for any substance, S-gas, liquid, S-solid, and the processes of vaporization and sublimation likewise involve increases in entropy, delta 0. Likewise, the reciprocal phase transitions, condensation, and deposition involve decreases in entropy, deltas zero. According to kinetic molecular theory, the temperature of a substance is proportional to the average kinetic energy of its particles. Raising the temperature of a substance will result in more extensive vibrations of the particles in solids and more rapid translations of the particles in liquids and gases. At higher temperatures, the distribution of kinetic energies among the atoms or molecules of the substance is also broader, more dispersed, than at lower temperatures. Thus, the entropy for any substance increases with temperature, figure 16. 11. Two graphs are shown. The y-axis of the left graph is labeled fraction of molecules, while the x-axis is labeled velocity v/m/s and has values of 0 through 1,500 along the axis with increments of 500. 4 lines are plotted on this graph. The first, labeled 100K, peaks around 200 m/s, while the second, labeled 200K, peaks near 300 m/s and is slightly lower on the y-axis than the first. The third line, labeled 500K, peaks around 550 m/s and is lower than the first two on the y-axis. The fourth line, labeled 1000K, peaks around 750 m/s and is the lowest of the four on the y-axis. Each line gets increasingly broad. The second graph has a y-axis labeled entropy, S, with an upward-facing arrow and an x-axis labeled temperature, K, and a right-facing arrow. The graph has 3 equally spaced columns in the background, labeled solid, liquid, and gas from left to right. A line extends slightly upward through the first column in a slight upward direction, then goes straight up in the transition between the first two columns. It then progresses in a slight upward direction through the second column, then goes up dramatically between the second and third columns, then continues in a slight upward direction once more. The first vertical region of this line is labeled melting, and the second is labeled boiling. Figure 16. 11 entropy increases as the temperature of a substance is raised, which corresponds to the greater spread of kinetic energies. When a substance undergoes a phase transition, its entropy changes significantly. Link to learning. Use interactive simulator to visualize the dependence of particle location and freedom of motion on physical state and temperature for several different atoms and molecules. The entropy of a substance is influenced by the structure of the particles, atoms, or molecules that comprise the substance. With regard to atomic substances, heavier atoms possess greater entropy at a given temperature than lighter atoms, which is a consequence of the relation between a particle's mass and the spacing of quantized translational energy levels, a topic beyond the scope of this text. For molecules, greater numbers of atoms increase the number of ways in which the molecules can vibrate, and thus the number of possible microstates and the entropy of the system. Finally, variations in the types of particles affects the entropy of a system. Compared to a pure substance, in which all particles are identical, the entropy of a mixture of 2 or more different particle types is greater. This is because of the additional orientations and interactions that are possible in a system comprised of non-identical components. For example, when a solid dissolves in a liquid, the particles of the solid experience both a greater freedom of motion and additional interactions with the solvent particles. This corresponds to a more uniform dispersal of matter and energy and a greater number of microstates. The process of dissolution, therefore, involves an increase in entropy, delta 0. Considering the various factors that affect entropy allows us to make informed predictions of the sign of deltas for various chemical and physical processes as illustrated in example 16. 3. Example 16. 3. Predicting the sign of S. Predict the sign of the entropy change for the following processes. Indicate the reason for each of your predictions. A. 1 mole liquid water at room temperature. 1 mole liquid water at 50 degrees C. B. Ag plus letter 1D44 letter 1D45E plus Cl minus letter 1D44 letter 1D45E Ag Cl letter 1D460. C. C6H6 letter 1D459 plus 152O2 letter 1D454 6 Co2 letter 1D454 plus 3H2O letter 1D459. D. NH3 letter 1D460 and H3 letter 1D459. Solution. A. Positive. Temperature increases. B negative, reduction in the number of ions particles in solution, decreased dispersal of matter. C negative, net decrease in the amount of gaseous species. D positive, phase transition from solid to liquid, net increase in dispersal of matter. Check your learning. Predict the sign of the entropy change for the following processes. Give a reason for your prediction. A na no 3, letter 1d460 na plus, letter 1d44 letter 1d45e, plus no 3 minus, letter 1d44 letter 1d45e. B, the freezing of liquid water. C co 2 letter 1d460 co 2, letter 1d454. D ca co 3 letter 1d460, ca o letter 1d460, plus co 2 letter 1d454. Answer. A positive, the solid dissolves to give an increase of mobile ions in solution. B negative, the liquid becomes a more ordered solid. C positive, the relatively ordered solid becomes a gas. D positive, there is a net increase in the amount of gaseous species. Learning objectives by the end of this section, you will be able to state and explain the second and third laws of thermodynamics, calculate entropy changes for phase transitions and chemical reactions under standard conditions, the second law of thermodynamics, in the quest to identify a property that may reliably predict the spontaneity of a process. A promising candidate has been identified. Entropy, processes that involve an increase in entropy of the system, delta zero, are very often spontaneous. However, examples to the contrary are plentiful. By expanding consideration of entropy changes to include the surroundings, we may reach a significant conclusion regarding the relation between this property and spontaneity. In thermodynamic models, the system and surroundings comprise everything, that is, the universe, and so the following is true. Delta letter 1d446 UNIV equals delta letter 1d446s plus delta letter 1d446er. To illustrate this relation, consider again the process of heat flow between two objects, one identified as the system and the other as the surroundings. There are three possibilities for such a process. The objects are at different temperatures, and heat flows from the hotter to the cooler object. This is always observed to occur spontaneously. Designating the hotter object as the system and invoking the definition of entropy yields the following. Delta letter 1d446 equals minus letter 1d45 rev, letter 1d447 cis and delta letter 1d446 equals letter 1d45 rev, letter 1d447 The magnitudes of minus qrev and qrev are equal. Their opposite arithmetic signs denoting loss of heat by the system and gain of heat by the surroundings. Since sized sewer in this scenario, the entropy decrease of the system will be less than the entropy increase of the surroundings, and so the entropy of the universe will increase. Delta letter 1d446 is delta letter 1d446 delta letter 1d446, UNIV equals delta letter 1d446 is plus delta letter 1d446 0. The objects are at different temperatures, and heat flows from the cooler to the hotter object. This is never observed to occur spontaneously. Again, designating the hotter object as the system and invoking the definition of entropy yields the following. Delta letter 1d446 is equals letter 1d45 rev, letter 1d447 cis and delta letter 1d446 equals minus letter 1d45 rev, letter 1d447 The arithmetic signs of qrev denote the gain of heat by the system and the loss of heat by the surroundings. The magnitude of the entropy change for the surroundings will again be greater than that for the system. But in this case, the signs of the heat changes, that is, the direction of the heat flow, will yield a negative value for delta SUNIV. This process involves a decrease in the entropy of the universe. The objects are at essentially the same temperature, size approximately tsur, and so the magnitudes of the entropy changes are essentially the same for both the system and the surroundings. In this case, the entropy change of the universe is 0, and the system is at equilibrium. Delta letter 1d446 is approximately delta letter 1d446 delta letter 1d446. UNIV equals delta letter 1d446 is plus delta letter 1d446 equals 0. These results lead to a profound statement regarding the relation between entropy and spontaneity, known as the second law of thermodynamics. All spontaneous changes cause an increase in the entropy of the universe. A summary of these three relations is provided in Table 16. 1. The second law of thermodynamics delta suniv, 0 spontaneous delta suniv, 0 non-spontaneous, spontaneous in opposite direction, delta suniv equals 0 at equilibrium. Table 16. 1. For many realistic applications, the surroundings are vast in comparison to the system. In such cases, the heat gained or lost by the surroundings as a result of some process represents a very small, nearly infinitesimal, fraction of its total thermal energy. For example, combustion of a fuel in air involves transfer of heat from a system, the fuel and oxygen molecules undergoing reaction, to surroundings that are infinitely more massive, the Earth's atmosphere. As a result, QSR is a good approximation of QRev, and the second law may be stated as the following. Delta letter 1d446 UNIV equals delta letter 1d446s plus delta letter 1d446er equals delta letter 1d446s plus letter 1d45er, letter 1d447. We may use this equation to predict the spontaneity of a process as illustrated in example 16. For example 16, 4 will ice spontaneously melt. The entropy change for the process H2O, letter 1d460, H2O, letter 1d459, is 22. 1 Jk and requires that the surroundings transfer 6 kJ of heat to the system. Is the process spontaneous at -10? C. Is it spontaneous at +10? C. Solution: we can assess the spontaneity of the process by calculating the entropy change of the universe. If delta suniv is positive, then the process is spontaneous. At both temperatures, delta S's equals 22, 1 Jk and QSR equals -6, Kj at -10. C. 263. 15K, the following is true. Delta letter 1d446, UNIV, equals delta letter 1d446s plus delta letter 1d446er equals delta letter 1d446s plus letter 1d45er letter 1d447 equals 22. 1J/K plus -6. 0 times 103J 263. 15K equals -0. 7Jk suniv 0, so melting is non-spontaneous, not spontaneous at -10 degrees C. At 10 C. 283 15K, the following is true. Delta letter 1d446 UNIV equals delta letter 1d446s plus letter 1d45er, letter 1d447 equals 22. 1J/K plus -6. 0 times 103J 283. 15K equals +0. 9Jk suniv 0, so melting is spontaneous at 10 degrees C. Check your learning using this information. Determine if liquid water will spontaneously freeze at the same temperatures. What can you say about the values of suniv? Answer. Entropy is a state function, so delta S freezing equals minus delta smelting equals -22. 1 Jk and QSR equals +6 Kj at -10. Degrees C spontaneous +0 7 Jk at +10. Degrees C non-spontaneous -0. 9 Jk. The third law of thermodynamics, the previous section, described the various contributions of matter and energy dispersal that contribute to the entropy of a system. With these contributions in mind, consider the entropy of a pure, perfectly crystalline solid possessing no kinetic energy. That is, at a temperature of absolute 0, 0K. This system may be described by a single microstate, as its purity, perfect crystallinity, and complete lack of motion means there is but one possible location for each identical atom or molecule comprising the crystal, W1. According to the Boltzmann equation, the entropy of this system is 0. Letter 1d446 equals letter 1d45 ln, letter 1d44a equals letter 1d45 ln. 1 equals 0. This limiting condition for a system's entropy represents the third law of thermodynamics. The entropy of a pure, perfect crystalline substance at 0K is 0. Careful calorimetric measurements can be made to determine the temperature dependence of a substance's entropy and to derive absolute entropy values under specific conditions. Standard entropies, S degrees, are for 1 mole of substance under standard conditions, a pressure of 1 bar, and a temperature of 298.15 K. See details regarding standard conditions in the thermochemistry chapter of this text. The standard entropy change, delta's degrees, for a reaction may be computed using standard entropies as shown below. Delta letter 1d446 degrees equals sum, letter 1d708, letter 1d446 degrees. Products, minus sum letter 1d708, letter 1d446 degrees. Reactants, where nu represents stoichiometric coefficients in the balanced equation representing the process. For example, delta's degrees for the following reaction at room temperature ABCD is computed as letter 1d465, letter 1d446 degrees, C, plus letter 1d466, letter 1d446 degrees, D, minus letter 1d45A, letter 1d446 degrees, A, plus letter 1d45B, letter 1d446 degrees, B. A partial listing of standard entropies is provided in Table 16. 2. And additional values are provided in Appendix G. The example exercises that follow demonstrate the use of S degrees values in calculating standard entropy changes for physical and chemical processes. Substance letter 1d446 degrees, Jmol minus 1K minus 1 carbon C, S, graphite, 5740 C, S, diamond, 238 Co, G, 197. 7 Co 2 G, 213. 8 CH4, G, 186. 3 CH4, G, 219. 3 CH6, G, 229. 2 CH3OL, 126. 8 C2H5OL, 160. 7 hydrogen H2, G, 130. 7 HG, 114. 7 H2O, G, 188. 8 H2OL, 70. 0 HCI, G, 186. 8 H2S, G, 205. 7 oxygen O2, G, 205. 2. Table 16. 2 standard entropies for selected substances measured at 1 atm and 298.15 K. Values are approximately equal to those measured at 1 bar, the currently accepted standard state pressure. Example 16. 5 determination of delta's degrees calculate the standard entropy change for the following process. HO. Solution calculate the entropy change using standard entropies as shown above. Letter 1d65, letter 1d446 degrees equals 1 mol, 70. 0 Jmol minus 1 K minus 1 minus 1 mol, 188. 8 Jmol minus 1 K minus 1 equals minus 118. 8 Jk, the value for delta's degrees is negative, as expected for this phase transition, condensation, which the previous section discussed. Check your learning, calculate the standard entropy change for the following process. H2, letter 1d454, plus C2H4, letter 1d454, C2H6, letter 1d454, answer. Minus 120. 6 Jk 1 mol 1 example 16. 6 determination of delta's degrees calculate the standard entropy change for the combustion of methanol, CH3O. 2 CH3O letter 1d459, plus 3O2, letter 1d4542 CO2, letter 1d454, plus 4 H2O, letter 1d459 solution, calculate the entropy change using standard entropies as shown above. Delta letter 1d446 degrees equals sum, letter 1d708, letter 1d446 degrees. Products, minus sum letter 1d708, letter 1d446 degrees. Reactants, 2 mol times letter 1d446 degrees, Co2, letter 1d454. Plus 4 mol times letter 1d446 degrees, H2. O, letter 1d459. Minus 2 mol times letter 1d446 degrees, CH3O, letter 1d459. Plus 3 mol times letter 1d446 degrees O. 8 plus 4 times 70. 0 minus 2, 126. 8 plus 3, 205. 2 equals minus 161. 6 Jk, check your learning, calculate the standard entropy change for the following reaction. Ka2S, Ka letter 1d460, plus H2O, letter 1d459, answer. 24. 7 Jk learning objectives. By the end of this section, you will be able to Define Gibbs free energy and describe its relation to spontaneity. Calculate free energy change for a process using free energies of formation for its reactants and products. Calculate free energy change for a process using enthalpies of formation and the entropies for its reactants and products. Explain how temperature affects the spontaneity of some processes. Relate standard free energy changes to equilibrium constants. One of the challenges of using the second law of thermodynamics to determine if a process is spontaneous is that it requires measurements of the entropy change for the system and the entropy change for the surroundings. An alternative approach involving a new thermodynamic property, defined in terms of system properties, only was introduced in the late 19th century by American mathematician Josiah Willard Gibbs. This new property is called the Gibbs free energy, G, or simply the free energy, and it is defined in terms of a system's enthalpy and entropy as the following. Letter 1d43a equals letter 1d43b minus letter 1d447 letter 1d446. Free energy is a state function, and at constant temperature and pressure, the free energy change, delta G, may be expressed as the following. For simplicity's sake, the subscript cis will be omitted henceforth. The relationship between this system property and the spontaneity of a process may be understood by recalling the previously derived second law expression. Delta letter 1d446 UNIV equals delta letter 1d446 plus letter 1d45 ESER, letter 1d447. The first law requires that QSER equals minus QSIS, and at constant pressure QSIS equals delta, so this expression may be rewritten as delta letter 1d446 UNIV equals delta letter 1d446 minus delta letter 1d43b, letter 1d447. Multiplying both sides of this equation by minus t and rearranging yields the following. Minus letter 1d447 delta, letter 1d446, UNIV equals delta letter 1d43b minus letter 1d447 delta letter 1d446. Comparing this equation to the previous one for free energy change shows the following relation. Delta letter 1d43a equals minus letter 1d447 delta, letter 1d446, UNIV, the free energy change, is therefore a reliable indicator of the spontaneity of a process, being directly related to the previously identified spontaneity indicator, delta SUNIV. Table 16. 3 summarizes the relation between the spontaneity of a process and the arithmetic signs of these indicators. Relation between process spontaneity and signs of thermodynamic properties, delta SUNIV 0 delta G, 0 spontaneous delta SUNIV, 0 delta G, 0 non-spontaneous delta SUNIV equals 0 delta G equals 0 at equilibrium. Table 16. 3 What's free about delta G? In addition to indicating spontaneity, the free energy change also provides information regarding the amount of useful work, W, that may be accomplished by a spontaneous process. Although a rigorous treatment of this subject is beyond the scope of an introductory chemistry text, a brief discussion is helpful for gaining a better perspective on this important thermodynamic property. For this purpose, consider a spontaneous exothermic process that involves a decrease in entropy. The free energy, as defined by delta letter 1d43a, equals delta letter 1d43b minus letter 1d447 delta letter 1d446, may be interpreted as representing the difference between the energy produced by the process, delta, and the energy lost to the surroundings, T deltas. The difference between the energy produced and the energy lost is the energy available, or free, to do useful work by the process, delta G. If the process somehow could be made to take place under conditions of thermodynamic reversibility, the amount of work that could be done would be maximal. Delta letter 1d43a equals letter 1d464 max, where letter 1d464 max refers to all types of work, except expansion, pressure volume work. However, as noted previously in this chapter, such conditions are not realistic. In addition, the technologies used to extract work from a spontaneous process, e.g., batteries, are never 100% efficient, and so the work done by these processes is always less than the theoretical maximum. Similar reasoning may be applied to a non-spontaneous process, for which the free energy change represents the minimum amount of work that must be done on the system to carry out the process. Calculating free energy change, free energy, is a state function, so its value depends only on the conditions of the initial and final states of the system. A convenient and common approach to the calculation of free energy changes for physical and chemical reactions is by use of widely available compilations of standard-state thermodynamic data. One method involves the use of standard enthalpies and entropies to compute standard free energy changes, delta degrees, according to the following relation. Delta letter 1d43a degrees equals delta letter 1d43b degrees minus letter 1d447, delta letter 1d446 degrees, example 16. 7. Using standard enthalpy and entropy changes to calculate delta degrees, use standard enthalpy and entropy data from Appendix G to calculate the standard free energy change for the vaporization of water at room temperature, 298 K. What does the computed value for delta degrees say about the spontaneity of this process? Solution: the process of interest is the following. H-O. The standard change in free energy may be calculated using the following equation. Delta letter 1d43a degrees equals delta letter 1d43b degrees minus letter 1d447 delta letter 1d446 degrees from Appendix G. Substance delta letter 1d43b f kj slash mol letter 1d446 degrees j slash k mol H2O L minus 285. 8370. H2O G minus 241. 82 188. 8. Using the appendix data to calculate the standard enthalpy and entropy changes yields. Delta letter 1d43b degrees equals delta letter 1d43b f H2O letter 1d454 minus delta letter 1d43b f H2O letter 1d459 equals minus 241. 82 kj slash mol minus 285. 83 kj slash mol equals 44. 1 kj delta letter 1d446 degrees equals 1 mol times letter 1d446 degrees H2O letter 1d454 minus 1 mol times letter 1d446 degrees H2O letter 1d459 equals 1 mol 188. 8j slash mol k minus 1 mol 70. 0j slash mol k equals 118. 8j k delta letter 1d43a degrees equals delta letter 1d43b degrees minus letter 1d447 delta letter 1d446 degrees. Substitution into the standard free energy equation yields. Delta letter 1d43a degrees equals delta letter 1d43b degrees minus letter 1d447 delta letter 1d446 degrees equals 44. 1 kj minus 298 k times 118. 8j slash k times 1 kj 1000j 44. 1 kj minus 35. 4 kj equals 8. 6 kj at 298 k, 25 degrees C. Delta letter 1d43a degrees 0, so boiling is non-spontaneous, not spontaneous. Check your learning use, standard enthalpy and entropy data from Appendix G to calculate the standard free energy change for the reaction shown here, 298 K. What does the computed value for delta degrees say about the spontaneity of this process? C to H6, letter 1d454, H2, letter 1d454, plus C to H4, letter 1d454 answer. Delta letter 1d43a degrees equals 102. 0 kj slash mol, the reaction is non-spontaneous, not spontaneous, at 25 degrees C. The standard free energy change for a reaction may also be calculated from standard free energy of formation, delta degrees values of the reactants and products involved in the reaction. The standard free energy of formation is the free energy change that accompanies the formation of 1 mole of a substance from its elements in their standard states. Similar to the standard enthalpy of formation, delta letter 1d43a, F, is by definition 0 for elemental substances in their standard states. The approach used to calculate delta letter 1d43a degrees for a reaction from delta letter 1d43a, F values, is the same as that demonstrated previously for enthalpy and entropy changes. For the reaction letter 1D45A, A plus letter 1D45B, B letter 1D465C, plus letter 1D466D. The standard free energy change at room temperature may be calculated as delta letter 1D43A degrees equals sum new delta letter 1D43A degrees, products, minus sum new delta letter 1D43A degrees, reactants, equals letter 1D465 delta letter 1D43A, F, C plus letter 1D466 delta letter 1D43A, FD minus letter 1D45A delta letter 1D43A, FA plus letter 1D45B delta letter 1D43A, FB. Example 16. 8. Using standard free energies of formation to calculate delta degrees, consider the decomposition of yellow mercury, Roman 2, oxide. HgO letter 1D460, yellow. Hg letter 1D459, plus 12O2 letter 1D454. Calculate the standard free energy change at room temperature, delta letter 1D43A degrees, using a standard free energies of formation and B standard enthalpies of formation and standard entropies. Do the results indicate the reaction to be spontaneous or non-spontaneous under standard conditions? Solution: the required data are available in Appendix G and are shown here. Compound delta letter 1D43A, F, Kj/mol delta letter 1D43B, FKj/mol, letter 1D446 degrees, J/K mol, HgOs, yellow minus 58, 43 minus 90, 4671, 13 Hg, L0075, 902 G 00252 A. Using free energies of formation. Delta letter 1D43A degrees equals sum letter 1D708 letter 1D43A F products minus sum letter 1D708 delta letter 1D43A F reactants equals 1 delta letter 1D43A FHG letter 1D459 plus 12 delta letter 1D43A FO2 letter 1D454 minus 1 delta letter 1D43A FHG O letter 1D460. Yellow equals 1 mol, 0 kj/mol, plus 12 mol 0 kj/mol minus 1 mol minus 58. 43 kj/mol equals 58. 43 kj/mol B, using enthalpies and entropies of formation. Delta letter 1D43B degrees equals sum letter 1D708, delta letter 1D43B, F products minus sum letter 1D708, delta letter 1D43B F reactants, equals 1 delta letter 1D43B, FHG letter 1D459, plus 12 delta letter 1D43B, FO2 letter 1D454 minus 1 delta letter 1D43B, FHG O letter 1D460. Yellow equals 1 mol, 0 kj/mol, plus 12 mol 0 kj/mol minus 1 mol minus 90. 46 kj/mol equals 90. 46 kj/mol letter 1D65 letter 1D446 degrees equals sum new delta letter 1D446 degrees. Products minus sum new delta letter 1D446 degrees. Reactants equals 1 delta letter 1D446 degrees Hg letter 1D459 plus 12 delta letter 1D446 degrees O2 letter 1D454 minus 1 delta letter 1D446 degrees Hg O letter 1D460. Yellow equals 1 mol, 75. 9 j/mol K plus 12 mol, 205. 2 j/mol K minus 1 mol, 71. 13 j/mol K equals 107. 4 j/mol K delta letter 1D43A degrees equals delta letter 1D43B degrees minus letter 1D447 delta letter 1D446 degrees equals 90. 46 kj minus 298. 15 k times 107. 4 j/k mol times 1 kj 1000 j delta letter 1D43A degrees equals 90. 46 minus 32. kj/mol equals 58. 45 kj/mol. Both ways to calculate the standard free energy change at 25 degrees C give the same numerical value to 3 significant figures, and both predict that the process is non-spontaneous, not spontaneous, at room temperature. Check your learning, calculate delta degrees, using a free energies of formation and B enthalpies of formation and entropies, Appendix G. Do the results indicate the reaction to be spontaneous or non-spontaneous at 25 degrees C? CH4, letter 1D454, H2, letter 1d454 plus C to H2, letter 1d454. Answer A. 140. 8 kJ/mol, non-spontaneous. B. 141. 5 kJ/mol, non-spontaneous free energy changes for coupled reactions, the use of free energies of formation to compute free energy changes for reactions as described above is possible because delta G is a state function, and the approach is analogous to the use of Hess' law in computing enthalpy changes. See the chapter on thermochemistry. Consider the vaporization of water as an example. H2O, letter 1d459, right arrow H2O, letter 1d454. An equation representing this process may be derived by adding the formation reactions for the two phases of water, necessarily reversing the reaction for the liquid phase. The free energy change for the sum reaction is the sum of free energy changes for the two added reactions. H2 letter 1d454 plus 12O2 letter 1d454, right arrow H2O letter 1d454, delta letter 1d43A F gas H2O letter 1d459, right arrow H2 letter 1d454 plus 12O2 letter 1d454, minus delta letter 1d43A liquid H2O, letter 1d459 right arrow H2O, letter 1d454, delta letter 1d43A F gas liquid. This approach may also be used in cases non-spontaneous reaction is enabled by coupling it to a spontaneous reaction. For example, the production of elemental zinc from zinc sulfide is thermodynamically unfavorable, as indicated by a positive value for delta degrees. ZnS, letter 1d460, right arrow Zn, letter 1d460, plus S letter 1d460, delta letter 1d43A, 1 equals 201. 3 kJ. The industrial process for production of zinc from sulfidic ores involves coupling this decomposition reaction to the thermodynamically favorable oxidation of sulfur. S letter 1d460 plus O2 letter 1d454 right arrow so 2 letter 1d454 delta letter 1d43A 2 equals minus 300. 1 kJ. The coupled reaction exhibits a negative free energy change and is spontaneous. ZnS letter 1d460 plus O2 letter 1d454 right arrow Zn letter 1d460 plus O2 letter 1d454 delta letter 1d43A degrees equals 201. 3 kJ plus minus 300. 1 kJ equals 98. 8 kJ. This process is typically carried out at elevated temperatures, so this result obtained using standard free energy values is just an estimate. The gist of the calculation, however, holds true. Example 16. 9. Calculating free energy change for a coupled reaction is a reaction coupling the decomposition of ZnS to the formation of H2S expected to be spontaneous under standard conditions. Solution following the approach outlined above and using free energy values from Appendix G. Decomposition of zinc sulfide. ZnS letter 1d460, right arrow Zn letter 1d460, plus S, letter 1d460, delta letter 1d43A, 1 equals 201. 3 kJ. Formation of hydrogen sulfide. S letter 1d460, plus H2 letter 1d454, right arrow H to S, letter 1d454, delta letter 1d43A, 2 equals minus 33. 4 kJ. Coupled reaction. ZnS, letter 1d460, plus H2, letter 1d454, right arrow Zn, letter 1d460, plus H to S, letter 1d454, delta, letter 1d43A, degrees equals 201. 3 kJ plus minus 33. 4 kJ equals 167. 9 kJ. The coupled reaction exhibits a positive free energy change and is thus non-spontaneous. Check your learning. What is the standard free energy change for the reaction below? Is the reaction expected to be spontaneous under standard conditions? Phi S, letter 1d460, plus O2 letter 1d454 right arrow Phi, letter 1d460, plus SO2, letter 1d454 answer. Minus 199. 7 kJ. Spontaneous temperature dependence of spontaneity. As was previously demonstrated in this chapter's section on entropy, the spontaneity of a process may depend upon the temperature of the system. Phase transitions, for example, will proceed spontaneously in one direction or the other depending upon the temperature of the substance in question. Likewise, some chemical reactions can also exhibit temperature-dependent spontaneities. To illustrate this concept, the equation relating free energy change to the enthalpy and entropy changes for the process is considered. Delta letter 1d43a equals delta letter 1d43b minus letter 1d447 delta letter 1d446. The spontaneity of a process, as reflected in the arithmetic sign of its free energy change, is then determined by the signs of the enthalpy and entropy changes and, in some cases, the absolute temperature. Since T is the absolute Kelvin temperature, it can only have positive values. 4 possibilities therefore exist with regard to the signs of the enthalpy and entropy changes. Both delta and deltas are positive. This condition describes an endothermic process that involves an increase in system entropy. In this case, delta will be negative if the magnitude of the T deltas term is greater than delta. If the T deltas term is less than delta, the free energy change will be positive. Such a process is spontaneous at high temperatures and non-spontaneous at low temperatures. Both delta and deltas are negative. This condition describes an exothermic process that involves a decrease in system entropy. In this case, delta will be negative if the magnitude of the T deltas term is less than delta. If the T deltas term's magnitude is greater than delta, the free energy change will be positive. Such a process is spontaneous at low temperatures and non-spontaneous at high temperatures. Delta is positive and deltas is negative. This condition describes an endothermic process that involves a decrease in system entropy. In this case, delta will be positive regardless of the temperature. Such a process is non-spontaneous at all temperatures. Delta is negative and deltas is positive. This condition describes an exothermic process that involves an increase in system entropy. In this case, delta will be negative regardless of the temperature. Such a process is spontaneous at all temperatures. These 4 scenarios are summarized in Figure 16. 12. A table with 3 columns and 4 rows is shown. The first column has the phrase, delta S greater than 0, increase in entropy, in the third row, and the phrase, delta S less than 0, decrease in entropy, in the fourth row. The second and third columns have the phrase, summary of the 4 scenarios for enthalpy and entropy changes, written above them. The second column has delta H greater than 0, endothermic, in the second row, delta G less than 0 at high temperature, delta G greater than 0 at low temperature, process is spontaneous at high temperature, in the third row, and delta G greater than 0 at any temperature, process is non-spontaneous at any temperature, in the fourth row. The third column has delta H less than 0, exothermic, in the second row, delta G less than 0 at any temperature, process is spontaneous at any temperature, in the third row, and delta G less than 0 at low temperature, delta G greater than 0 at high temperature, process is spontaneous at low temperature. Figure 16. 12. There are 4 possibilities regarding the signs of enthalpy and entropy changes. Example 16. 10. Predicting the temperature dependence of spontaneity. The incomplete combustion of carbon is described by the following equation. 2C letter 1d460 plus O2 letter 1d4542 co-letter 1d454. How does the spontaneity of this process depend upon temperature? Solution. Combustion processes are exothermic, delta 0. This particular reaction involves an increase in entropy due to the accompanying increase in the amount of gaseous species, net gain of 1 mole of gas, delta 0. The reaction is therefore spontaneous, delta 0, at all temperatures. Check your learning. Popular chemical hand warmers generate heat by the air oxidation of iron. 4 Fe letter 1d460 plus 3O2 letter 1d4542 Fe2O 3 letter 1d460. How does the spontaneity of this process depend upon temperature? Answer. Delta and deltas are negative. The reaction is spontaneous at low temperatures. When considering the conclusions drawn regarding the temperature dependence of spontaneity, it is important to keep in mind what the terms high and low mean. Since these terms are adjectives, the temperatures in question are deemed high or low relative to some reference temperature. A process that is non-spontaneous at one temperature but spontaneous at another will necessarily undergo a change in spontaneity. as reflected by its delta, as temperature varies. This is clearly illustrated by a graphical presentation of the free energy change equation, in which delta is plotted on the y-axis versus T on the x-axis. Delta letter 1d43a equals delta letter 1d43b minus letter 1d447, delta letter 1d446. Such a plot is shown in Figure 16. 13. A process whose enthalpy and entropy changes are of the same arithmetic sign will exhibit a temperature-dependent spontaneity as depicted by the two yellow lines in the plot. Each line crosses from one spontaneity domain, positive or negative delta, to the other at a temperature that is characteristic of the process in question. This temperature is represented by the x-intercept of the line, that is, the value of T for which delta is 0. Delta letter 1d43a equals 0 equals delta letter 1d43b minus letter 1d447, delta letter 1d446. Letter 1d447 equals delta letter 1d43b, delta letter 1d446. So, saying a process is spontaneous at high or low temperatures means the temperature is above or below, respectively, that temperature at which delta for the process is 0. As noted earlier, the condition of delta equals 0 describes a system at equilibrium. A graph is shown where the y-axis is labeled free energy and the x-axis is labeled increasing temperature, K. The value of 0 is written midway up the y-axis with the label delta G greater than 0, written above this line, and delta G less than 0, written below it. The bottom half of the graph is labeled on the right as spontaneous, and the top half is labeled on the right as non-spontaneous. A green line labeled delta H less than 0, delta S greater than 0, extends from a quarter of the way up the y-axis to the bottom right of the graph. A yellow line labeled delta H less than 0, delta S less than 0, extends from a quarter of the way up the y-axis to the middle right of the graph. A second yellow line labeled delta H greater than 0, delta S greater than 0, extends from 3/4 of the way up the y-axis to the middle right of the graph. A red line labeled delta H greater than 0, delta S less than 0, extends from 3/4 of the way up the y-axis to the top right of the graph. Figure 16. 13. These plots show the variation in delta with temperature for the 4 possible combinations of arithmetic sign for delta and deltas. Example 16. 11. Equilibrium temperature for a phase transition. As defined in the chapter on liquids and solids, the boiling point of a liquid is the temperature at which its liquid and gaseous phases are in equilibrium. That is, when vaporization and condensation occur at equal rates. Use the information in Appendix G to estimate the boiling point of water. Solution. The process of interest is the following phase change. H2O, letter 1d459 H2O, letter 1d454. When this process is at equilibrium, delta equals 0, so the following is true. Equals delta letter 1d43b, degrees minus letter 1d447 delta, letter 1d446 degrees, or letter 1d447 equals delta letter 1d43b, degrees delta letter 1d446 degrees. Using the standard thermodynamic data from Appendix G, delta letter 1d43b degrees equals 1 mol times delta letter 1d43b FH2O, letter 1d454. Minus 1 mol times delta letter 1d43b FH2O, letter 1d459. 1 mol minus 241. 82 kJ/mol minus 1 mol minus 286. 83 kJ/mol equals 44. 1 kJ. Delta letter 1d446 degrees equals 1 mol times delta letter 1d446 degrees H2O, letter 1d454. Minus 1 mol times delta letter 1d446 degrees H2O, letter 1d459. 1 mol 188. 8 J/K mol minus 1 mol 70. 0 J/K mol equals 118. 8 JK. Letter 1d447 equals delta letter 1d43b. Degrees delta letter 1d446 degrees equals 44. 0 1 times 103 J 118. 8 J/K equals 370. 5 K equals 97. 3 degrees C. The accepted value for water's normal boiling point is 373. 2K, 100, 0 degrees C, and so this calculation is in reasonable agreement. Note that the values for enthalpy and entropy changes data used were derived from standard data at 298K, Appendix G. If desired, you could obtain more accurate results by using enthalpy and entropy changes determined at or at least closer to the actual boiling point. Check your learning. Use the information in Appendix G to estimate the boiling point of CS2. Answer 313K. Accepted value 319K. Free energy and equilibrium. The free energy change for a process may be viewed as a measure of its driving force. A negative value for deltig represents a driving force for the process in the forward direction, while a positive value represents a driving force for the process in the reverse direction. When deltig is 0, the forward and reverse driving forces are equal, and the process occurs in both directions at the same rate. The system is at equilibrium. In the chapter on equilibrium, the reaction quotient, Q, was introduced as a convenient measure of the status of an equilibrium system. Recall that Q is the numerical value of the mass-action expression for the system, and that you may use its value to identify the direction in which a reaction will proceed in order to achieve equilibrium. When Q is lesser than the equilibrium constant, K, the reaction will proceed in the forward direction until equilibrium is reached and Q equals K conversely. If QK, the process will proceed in the reverse direction until equilibrium is achieved. The free energy change for a process taking place with reactants and products present under non-standard conditions, pressures other than 1 bar, concentrations other than 1 m, is related to the standard free energy change according to this equation. Delta letter 1 D43A equals delta letter 1 D43A plus letter 1 D445, letter 1 D447 ln, letter 1 D444. R is the gas constant, 8, 314 J/K mol, T is the Kelvin or absolute temperature, and Q is the reaction quotient. For gas phase equilibria, the pressure-based reaction quotient, QP, is used. The concentration-based reaction quotient, QC, is used for condensed phase equilibria. This equation may be used to predict the spontaneity for a process under any given set of conditions, as illustrated in Example 16. 12. Example 16. 12. Calculating deltig under non-standard conditions. What is the free energy change for the process shown here under the specified conditions? T equals 25 degrees C, letter 1D443N2 equals 0. 870 atm. Letter 1D443H2 equals 0. 250 atm. And letter 1D443NH3 equals 12. 9 atm. 2NH3. Letter 1D4543H2. Letter 1D454 plus, N2 letter 1D454 delta letter 1D43A, degrees equals 33. 0 kJ/mol. Solution. The equation relating free energy change to standard free energy change and reaction quotient may be used directly. Delta letter 1D43A equals delta letter 1D43A plus, letter 1D445, letter 1D447 ln, letter 1D444 equals 33. 0 kJ mol plus 8, 314 J mol K times 298 K times ln 0, 2503 times 0, 87,012. 92 equals 9,680 J mol or 9. 68 kJ/mol. Since the computed value for deltig is positive, the reaction is non-spontaneous under these conditions. Check your learning. Calculate the free energy change for this same reaction at 875 degrees C for a mixture containing each gas at a partial pressure of 188 atm. Is the reaction spontaneous under these conditions? Answer. Deltig equals 45.1 kJ/mol. Now, for a system at equilibrium, Q equals K and deltig equals 0, and the previous equation may be written as equals delta letter 1D43A degrees plus letter 1D445, letter 1D447 ln, letter 1D43 at equilibrium. Delta letter 1D43A degrees equals minus letter 1D445, letter 1D447 ln, letter 1D43. OR letter 1D43 equals letter 1D452 minus delta letter 1D43A degrees letter 1d445 letter 1d447. This form of the equation provides a useful link between these two essential thermodynamic properties, and it can be used to derive equilibrium constants from standard free energy changes and vice versa. The relations between standard free energy changes and equilibrium constants are summarized in Table 16. 4. Relations between standard free energy changes and equilibrium constants. K delta G degrees composition of an equilibrium mixture. 1 0 products are more abundant. 1 reactants are more abundant. Equals 1 equals 0 reactants and products are comparably abundant. Table 16. 4. Example 16. 13. Calculating an equilibrium constant using standard free energy chain. Given that the standard free energies of formation of Ag plus AC, Cl minus AC, and Ag ClS are 77, 1 kJ/mol minus 131, 2 kJ/mol and minus 109, 8 kJ/mol, respectively, calculate the solubility product, KSB, for AgCl. Solution. The reaction of interest is the following. AgCl, letter 1d460 Ag plus, letter 1d44 letter 1d45e plus, Cl minus, letter 1d44 letter 1d45e, letter 1d43sb equals Ag plus Cl minus. The standard free energy change for this reaction is first computed using standard free energies of formation for its reactants and products. Delta letter 1d43a degrees equals delta letter 1d43a, F Ag plus letter 1d44 letter 1d45e, plus delta letter 1d43a, F Cl minus letter 1d44 letter 1d45e minus delta letter 1d43a, F Ag Cl letter 1d460 equals 77. 1 kJ/mol minus 131, 2 kJ/mol minus 109, 8 kJ/mol equals 55, 7 kJ/mol. The equilibrium constant for the reaction may then be derived from its standard free energy change. Letter 1d43sb equals letter 1d452 minus delta letter 1d43a degrees letter 1d445 letter 1d447 equals exp minus delta letter 1d43a degrees letter 1d445 letter 1d447 equals exp minus 55. 7 times 103j/mol 8, 314j/mol k times 298, 15k equals exp minus 22. 470 equals letter 1d452 minus 22. 470 equals 1. 74 times 10 minus 10. This result is in reasonable agreement with the value provided in Appendix J. Check your learning. Use the thermodynamic data provided in Appendix G to calculate the equilibrium constant for the dissociation of dinitrogen tetroxide at 25 degrees C. To note 2, letter 1d454 and to 04, letter 1d454. Answer, K equals 0.32. To further illustrate the relation between these two essential thermodynamic concepts, consider the observation that reactions spontaneously proceed in a direction that ultimately establishes equilibrium. As may be shown by plotting the free energy versus the extent of the reaction, for example, as reflected in the value of Q, equilibrium is established when the system's free energy is minimized, figure 16. 14. If a system consists of reactants and products in non-equilibrium amounts, Q not equal to K, the reaction will proceed spontaneously in the direction necessary to establish equilibrium. 3 graphs labeled A, B, and C are shown where the y-axis is labeled Gibbs free energy G and G superscript degree sign reactants, while the x-axis is labeled reaction progress and reactants on the left and products on the right. In graph A line begins at the upper left side and goes steadily down to a point about halfway up the y-axis and 2/3 of the way on the x-axis, then rises again to a point labeled G superscript degree sign products. That is slightly higher than halfway up the y-axis. The distance between the beginning and ending points of the graph is labeled as delta G less than 0, while the lowest point on the graph is labeled Q equals K greater than 1. In graph B, a line begins at the middle left side and goes steadily down to a point about 2/5 up the y-axis and 1/3 of the way on the x-axis, then rises again to a point labeled G superscript degree sign products. That is near the top of the y-axis. The distance between the beginning and ending points of the graph is labeled as delta G greater than 0, while the lowest point on the graph is labeled Q equals K less than 1. In graph C, a line begins at the upper left side and goes steadily down to a point near the bottom of the y-axis and halfway on the x-axis, then rises again to a point labeled G superscript degree sign, products, that is equal to the starting point on the y-axis, which is labeled G superscript degree sign, reactants. The lowest point on the graph is labeled Q equals K equals 1. At the top of the graph is the label delta G superscript degree sign equals 0. Figure 16. 14. These plots show the free energy versus reaction progress for systems whose standard free energy changes are a negative, B positive, and C 0. Non-equilibrium systems will proceed spontaneously in whatever direction is necessary to minimize free energy and establish equilibrium.